welcome back. We're in the last stretch. We can do this. Now we need to do some calculations, okay? So we still look in the conservation of energy, and we're going to look at a couple of examples. Here's the first one. We have a ball of mass 1 kilogram moving east at 2 meters per second. Another ball of mass 1.5 kilograms is moving west at 1.5 meters per second. The balls collide head-on. After the collision, the 1 kilogram ball rebounds. Rebounds means that it changes direction. So it was going east, now it's going to be going west with a velocity of 2.05, and the 1.5 kilogram, rebounds at 1.2. So it was going west, now it's going east. They've been really nice in this question because they've given you both before velocities and they've given you both after velocities. There's a reason for it because we're trying to just get to the kinetic energy part of this, okay? So, what's the situation? We have a 1 kilogram block, okay, that's moving east, and they said to me that it was moving east at 2. It then collides with a 1.5 kilogram block that's moving west at 1.5. Then they collide. There's my collision. I'm going to do the after over here. The 1 kilogram rebounds, so it's going in that direction, and they said it was 2.05. And the 1.5 rebounds, so now it's going east, and let's just check. It said it was at 1.2. So that's our situation. Just because now we're going to be looking at kinetic energy doesn't mean we can ignore direction, okay? Velocity is still a vector. As a vector, it needs to have direction. We need to make a decision. I'm going to make east positive simply because, so that's my positive direction, simply because east was given first. If they had said block A was going west, and that was the first thing they told me about, I would have made west my positive direction. You can choose, it's up to you. I just like to stick to something that's the same with every question. Original direction, positive. So, that means for us, because that's going west, the 1.5 is going at minus 1.5 meters per second, and after the collision, the 1 kilogram is going at minus 2.05. Always write that in, because it's these little things like the direction, like the negative, that costs you marks because it's considered the simple things. Sometimes it doesn't feel like it, but they are considered the simple things, so we've got to take it into consideration. Now, question says, calculate the kinetic energy before the collision. We're leading you a little bit. Before the collision, so sum of the kinetic energy is going to be the first ball's initial velocity squared times its mass times a half, plus a half times the second ball's mass times the second ball's initial velocity squared. We have a half times 1 times 2 plus, and that's squared. Please don't forget the squared. I see that all the time. In fact, I almost forgot. A half, and then it's 1.5. Now we take note. Its velocity was west. West is negative. I have to substitute in the negative. I know that when I go 1.5, negative 1.5 squared, I'm going to get a positive answer. That's not the point. Velocity is a vector. When I substitute in the vector, I have to keep the negative as part of that. Now, we're going to use our calculators. I could do the first part of the sum in my head, but I can't do the other because the 1.5. So, let's just put this over here so I've got everything. So I have 0.5 times 1 times 2 squared plus 0.5, whoopsie, let's make sure you've got the 5, 0.5 times 1.5, 5 times, let's do the bracket, minus 1.5 squared, close the bracket, equal. I get a positive answer, and it's 0.3125. So, here I've put 4 decimal places because it is a very small kinetic energy. The instructions in your exam are to round off to at least 2 decimal places for your final answer. Yes, this is a final answer, but because it's exactly 4 decimal places, I'm going to keep it. Sometimes in these questions, the change in energy is so small that if you round off too early and have too few decimal places, you won't see it. So just be careful, all right? I'm going to keep the 4. Now, that's the first one. So that's the kinetic energy before the collision. Now they say, oops, I skipped this page, the kinetic energy after the collision. So I'm going to do exactly the same thing. I'm going to calculate, but now I'm looking at final velocity plus final velocity squared. So that means I've got a half, and the first ball was 1 kilogram, and now after the collision, it's going at minus 2.05. Remember, it changed direction. Then we have a half, 1.5, and now this is going at 1.2, and it's squared. There is no way I can do this in my head, and my maths isn't bad, okay? Please use your calculators. Now, there probably is someone or more than one of you who can do this in your head, and that's impressive, okay? I can't. So, calculator. Here we go. Let's clear what we had. So we're going to go 0.5 times 1 times negative 2.05 squared. We're going to add that to the 0.5 times 1.5 times 1.2 squared. There we go. And, ooh, I've made a mistake. Can you see? I got a negative answer, and I shouldn't have. So let's see where I would have made the mistake, and I think it's here. Okay, and it's important that we get this. So what I'm going to do is I'm going to take that negative away from that, and I'm actually going to put the square there, so it's part of the bracket. Okay? Much better. Positive answer, it's what I expected. Oh dear, that's not what I expected. So, we need to go look at some things again, because when I look at this, I go, first of all, now I'm going to get, and I want you to see this, okay? Oopsie, wrong way. Here, we got 3, let's just go back to this, 3,18125. Now, that makes sense. If I go back here, I got 0,3125. Something's not right here. So let's do this one again. I think what I did, okay, is I didn't square that 2. And that's fine. This is why we go back and check. So we've got 0.5 times 1 times 2 squared plus 0.5 times 1.5 times minus 1.5 squared There we go. Okay, now that makes more sense. Okay, so now we've got 3,685. So let's just fix this. And you know what? We all make mistakes, and it's fine. It really isn't a problem. So let's just go back and look again. 3,6875. So let's put that in, not with the eraser. Here we go. 3,6875 joules. Okay. Now, how did I know I'd made a mistake? Because it collided, not exploded, and the kinetic energy got bigger. Not going to happen in a collision. It's not possible, okay? And it's a big difference. So I knew there was a mistake, and it's important that you see that. So then it went to 3,1825. So now it's got smaller. Not by much, but it got smaller. We're okay with that. Next question. Is the collision elastic or inelastic? And then they say, explain your answer. It's an easy explanation. The kinetic energy before the collision is not equal to the kinetic energy after. It doesn't matter whether the after kinetic energy is bigger or smaller than the before kinetic energy. That is not the point here. The point is they are not equal. So, the answer is, it is an inelastic collision. Why? Because the sum of the kinetic energy before is not equal to the sum of the kinetic energy after. Explanation. Nice and simple. Didn't want a lot, didn't need to explain anything. They just wanted to know why we know it's inelastic. Now comes the next part. Now they ask you, why did the kinetic energy change? What they're asking you here is this. Because we know energy is always conserved. We can't lose energy, it changes form. Here, the kinetic energy didn't stay the same. What has happened to the kinetic energy? So what we want here is the kinetic energy is transformed into sound. We hear the collision and heat, okay, because there'll be friction. Definitely those two. Plus, now the third one is a little bit different, and it can be transferred into what we call deformation energy. This is a new one, okay, and this one's a hard one. No matter how hard the objects are, let me just put this down. When they collide with each other, they will deform a little bit, okay? They squash. That squashing takes energy, takes effort. So that's the deformation energy, okay? Even hard objects deform a little bit, okay? Everything does it, especially if they hit hard enough. You just can't see it with the naked eye. Sometimes, we can also get a transfer of energy in the form of light. Okay, that's not going to happen often. It won't happen with, it really only happens if they're metal. Okay, because when metal strikes metal, we can get sparks. So sometimes there's light, but really there's always going to be sound, there's going to be heat, and there's a little bit of deformation energy. All right, so that's where the kinetic energy went. Now, and I've mentioned this, is it possible for the kinetic energy of a system to increase? Everything we've done so far today has shown the kinetic energy getting smaller. So now we've got to go, okay, if the kinetic energy increases, it's definitely an inelastic collision. But for the kinetic energy to increase, it means that the velocities need to increase somewhere. And it's absolutely possible when there's an explosion, okay, like a gun. Because if we have two objects, so the answer here is yes, okay? If we have two objects that are together, so they're stationary together, this initial velocity is 0. So at the moment, this system has no kinetic energy. If I now exert a force on them, so say I push down on them or there's a spring between them, and I let that go, and now the two objects go off in a different direction, so they split. What happens now? Now, they both have a kinetic energy. It doesn't matter that they're in opposite directions, because remember, it's a square. So they just disappear, but now they didn't have. So over here, my kinetic energy is 0 at the beginning. Now, it absolutely is going to have a kinetic energy. That should actually be bigger than 0. It's going to increase. So, what am I telling you here? Please be careful. If it is an explosion, so the two objects were one to start off with, it is possible for the kinetic energy to increase if they were stationary at the beginning. When we've got two objects that are colliding, okay, then the kinetic energy can't increase because we're going to lose to sound and that sort of thing. Why am I telling you this? Because I don't want you to get a fright when you do a calculation and you end up increasing the kinetic energy. Because it's possible. Just look at the whole situation. Look at it in context. Okay, so what have we learned today? In an elastic collision, an inelastic collision, the total kinetic energy is not conserved. Total kinetic energy before is not equal to kinetic energy after. For an elastic collision, kinetic energy is conserved. Total before equals total after. Very, very, very rare. Okay? You're not going to come across those often. And that brings us to the end of today's lesson. Hopefully you've learned a lot, and that's all I have to say for today, so I'll see you again next time.